In this video, I just want to show you a quick example of using the formula to calculate heat. So we have here, you put a gallon of milk in the refrigerator and you cool it down from 45 Fahrenheit to 34 Fahrenheit. How much energy did you actually have to remove in order for that to happen? Okay, so what you want to do here, what you should think of first of all is that the amount of energy removed is going to be the heat that the milk gives off into its environment. And the heat can be calculated by this formula MC delta T. So just plugging into that formula, we're going to have M is 3.91 Fahrenheit. I mean, sorry, 3.91 kilograms. C is going to be 3.93 kilojoules per kilogram Kelvin. Now, I should probably say a few words about the units of specific heat. Let me just do it over off to the side here. So we have here the specific heat is 3.93 kilojoules divided by kilograms times Kelvin. That's like a typical way that these are reported. One thing I should note, first of all, if you look up these numbers from different sources, you can also report this number equally well as kilojoules over kilogram times degrees Celsius. It makes no difference in this case whether you use Kelvin or Celsius. And the reason why is because this is all about delta T's here. Okay, temperature in Celsius is obviously not equal to temperature in Kelvin, but changes in temperature are the same in Celsius and Kelvin. If something goes up by 10 degrees Celsius, it also goes up by 10 Kelvin. So it doesn't make any difference in this particular concept, Kelvin versus Celsius, because it's always talking about a change in temperature, never an absolute temperature. And by exactly the same argument, when you calculate delta T there, it doesn't matter if you calculate the delta T in Kelvin or in Celsius. Just as a general rule, if you're working with delta T's, Kelvin and Celsius are the same. If you're working with T, they're not the same. So be very conscientious about that. If you have a formula where you just have T by itself, it will make a difference if you're in Celsius or Kelvin. So you have to know what you're doing. In most scientific formulas, I think, at least in physics, they assume that you're going to be in Kelvin. But for this kind of a formula, it doesn't matter if you want to use Celsius. Okay, anyways. Oh, the other thing about this is it's in kilojoules per kilogram Kelvin. So we've got to convert that to SI units, which would be joules per kilogram Kelvin. So multiply by 1,000, it becomes 3930 joules per kilogram Kelvin. And then delta T is, as usual, just final minus initial. So the final here is 1.11 degrees Celsius. The initial is 7.22 degrees Celsius. And although it might look weird that I have Celsius on the right and Kelvin on the left, those will in fact cancel out for the reason that I just mentioned. So if I crunch these numbers here, I've got 1.11 minus 7.22, and then multiply that by 3930, multiply that by 3.91, and I get minus 93888 joules, which I just wanted to write out longhand to emphasize. This should probably be to you a shockingly large answer, 94,000 joules for this incredibly simple, incredibly mundane process. One thing that you need to learn to appreciate is that when it comes to thermal energy, the amount of energy you're working with is staggeringly high compared to mechanical energy most of the time. When we're making this point that thermal energy exists and that everything at the microscopic level is actually vibrating a little bit, it sounds like a very pedantic statement, like who really cares? Like, come on, that's just a small correction. It's not a small correction, because as it turns out, the amount of energy that's stored in this microscopic vibrations is huge. It's so huge that even small changes in temperature can be enough to overwhelm the amount of mechanical energy that you're working with. So that's something that you need to be conscientious about. A few comments then. The negative sign that we got in front of this Q, that negative sign means the fact that the energy is flowing out of the milk, because what we calculated here is the Q of the milk, not of the air in the refrigerator. So Q of the milk is negative 94,000 joules because it's giving off energy. Q of the air inside the refrigerator is positive 94,000 joules. The air in the refrigerator is absorbing this energy, and the air in the refrigerator is heating up, which then that energy has to be pumped out by the refrigerator, which is something we're not going to get into here. But so, to answer the question exactly, it actually says how much energy was removed from the milk. So there were 94,000 joules of energy removed from the milk, which is why it's negative, means removed 94,000 joules.